Okay, so there we go. So first question is a good one. It's basically they're going to have us in these first few questions work backwards from a table of data, like x, y values. It says x and f of x, but you know f of x is just y, huh? So it's a bunch of values, and it's from there, can you work backwards and answer the question, is this thing linear? Is it exponential, or is it neither? So we want to be able to look at a table of values and decide, is that a linear function like a straight line? Is it exponential, or is it neither? Well, how you determine it is you look at the y values. And let me just give you the two rules. If the y values add or subtract the same number, then it's linear. It's y equals mx plus b. The m is that number that they add, subtract every time. And the b is the number next to x is 0. That's one rule. Now, if, secondly, this is case number 1, it's a linear, this is the linear case. If, so over here is the exponential, if the y values multiply or divide. Multiply and dividing is the same thing, right? You multiply by the upside down, that's called dividing. Multiply by 1/2, that's the same as dividing by 2, right? Multiplying and dividing are the same thing. Just like adding and subtracting are the same thing. If you add a negative, that's subtraction. So we put those together in all situations in math. Multiplying, dividing, same thing. So if y values are multiplied divided by the same number, then that's exponential. And that means the formula is y equals c times b to the x, or whatever. You know, c and b are just made up letters, where the b, base, is that number multiplied, divided each time, and the c is the number next to x is 0, kind of like for the linear. So those are the rules. If you want to write down those two rules, and if it doesn't fit one of those, it's neither. So that's how you know. You look at it down. We'll do it on 4 examples in a row, and you'll get it real well, I think. It's not bad once you got that down. There's 2 sets of rules. Something's linear if it's adding or subtracting the same number every time. It's exponential if it's multiplying, dividing the same number every time. So let's go over here and look at the y values. 6 becomes 12. There's 2 ways you could do that. You could add 6, or you could multiply by 2. How do you know which one? Well, we're trying to look for the same pattern every time. What does it do on the next one? Does it add 6 again? No, it's multiplying by 2. So it looks like it's a times 2, but it soon fails. And then we'll say, nope, answer neither. So this one's a neither, because it neither adds 6 every time. That fails right away. Nor does it multiply by 2 every time. That works for a couple of steps, but then falls apart. So this function is neither exponential nor linear. It's not adding the same number every time, nor is it multiplying the same number every time. Do y'all see why adding the same number every time would be linear? Because that's what a line does, right? Every time you go over another x value, -1, 0, 1, 2, 3, right? You go over, up, over, up, over, up. You always go up the same amount. You add the same y. That's called the slope. That's why adding the same amount works. An exponential just multiplies the same number every time. Anyway, this one's neither. Make sense? Ready for another one? So number 2, take a look at these y values. Ask yourself, what's going on with the y values? Boom. And the first one's a fraction. If that bugs you, just look at the second one. How does 1 become 10? How does 10 become 100? How does 100 become 1,000? What's going on from y value to y value there? Yeah, it's timesing. That even works for the first one, doesn't it? It's timesing by 10 every time, isn't it? Right? 1/10 times 10 is 1. 1 times 10 is 10, times 10 is 100, times 10 is 1,000. So it's the same number being multiplied. So what does that mean? Which one is it? Linear, exponential, or neither? It's exponential. Now, they want me to say more than just it's exponential, then they want the equation. So what did I tell you about the equation? It's y equals c times b to the x. Put that in your 3x5 card for the test next Wednesday, Thursday. And now, the b, the base, is that number that's being multiplied every time. So that's the 10. 10 to the x. Good so far. That number being multiplied every time is the base, is the b. That's what those instructions on the other page said. And how do you find the c? Yeah, you go to the x equals 0 and you look right next to it and say, oh, it's 1. So really it's just 10 to the x. The 1 does nothing, so the answer is just 10 to the x. Because the c, what's next to x0, is just 1. Does that make sense? Do you see why I'm saying it's the number next to x0? If I take the equation y equals 1 times 10 to the x, and I plug in x is 0, like I'm making a table, say, whoops, making a table, xy table here, and I plug in x0, what are you going to get? 1 times 10 to the 0. What's anything to the 0 power, do you remember? 1. It's just 1, so you see you just get that number in the front, don't you? You see why that number in the front just ends up being whatever's next to x0? Because when you plug in x0, the power thing drops away. It becomes 1, right? That's why that rule will always work. Good, so we're done with this one. Questions on that one? So how about that one? Let's check out the y values. How does that become that? 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 Now, those are big numbers. I don't know it off the top of my head either. But you know what you could do to figure out what's being multiplied? You could divide on your calculator, right? Because if you divide, that tells you what was multiplied. So, for example, you could grab anywhere you want. You could grab the 156, and you could divide it there by the 13 and say, hey, what? That will tell you what was multiplied. Is it 12? Yeah. That tells you, oh, they multiplied by 12. 13 times 12 is 156. Now, does that keep working? Does that work for all of them? If I go times 12 again, 156 times 12, is that 1872? Use your calculator, it'll say yes. Times 12, does that work again? Yes. How about the very first one? 13 twelfths times 12? Yeah, the 12s cancel, huh? And it's just 13. Yeah. They're multiplying by 12 every time. See how we figured that out? By dividing. Can you write the equation real quick then? Equation is c times b to the x. What's the b? The b is the 12. It's that number being multiplied every time. What's the c? Yeah, it's the number across from 0. So it's 13 times 12 to the x. You could plug into the table. That would give you any of those values. Like if I plugged in x is 2, for example. X is 2. That would be 13 times 12 squared. Hit the buttons on your calculator. Guess what you're going to get? 1872. You're going to get the thing next to x is 2. See, that formula is the formula producing the values in the table. Does that make sense? It's an exponential equation. So we're able to work backwards from a table to a formula. That's kind of a somewhat powerful mathematical skill there. Good? Questions on that one? That's all that we haven't done. All right, so you know it's going to be linear. Prove it so, and find the equation. Look at those y values. What's happening from y value to y value? Is that homework last night okay? What was it, 5.2? I've already forgotten. What was 5.2? Oh, it was one-to-one functions and inverses. All right, hopefully that wasn't too bad. All right, so what's happening y value to y value? We're adding the same number every time, huh? We're adding 5 every time. So it's linear, which means it's y equals mx plus b. So we got to find the m and the b. What's the m? That is the 5. That is the slope, the amount you're adding every time. Now, how do you find the b? Next to 0. 8, right? Because if you plug in x to 0, you see you just get the number on the right, don't you? So there it is. It's a linear, there's the linear equation. That'll produce, check it out if you're not sure, like plug in x is 3. If you plug in x is 3, what are you going to get? 5 times 3 plus 8, 15 plus 8, it's at 23. Sure enough, that's what's next to x is 3, huh? That's the formula producing the values in the table. Good? All is well on that? So you can go from tables. I like that. You know me, no secrets. I like that. It's for sure on the test, right? There's one of those on exam 2 next week. It's on the practice exam. So make sure you can do that. So I'm going to jump forward a little bit here to number 9. All right, so there's our equation. So we're getting a new kind of graph now, exponential graph. We're going to add 2 new graphs today and tomorrow to our ability to graph things. You know those original 6 we learned? You know, the absolute value, v, and the square root, and the x squared, and the cube root, and the 1 over x. Those original 6. Now we're going to start slowly adding, not many more, probably maybe 4 more throughout the semester to those basic 6. Probably have about 10 when we're done. So here we're going to add exponential. So you want to learn the basic look of exponential. Let me give that to you. If you have y equals a plus b to the x. Now notice, I know this can be confusing because I just did the table thing. So it's not like the table. For the table, I gave you y equals c times b to the x. Now in reality, yeah, maybe I should put that in there. I try to make it simple, but then I don't want to oversimplify and confuse you. All right, so let me just take, there's what we did for the table, c times b to the x. I'm throwing in an extra a. They didn't do that in the table. I knew they weren't going to do that, so I didn't bother you with it. But in real life, they can throw a number added or subtracted, and they often will when it comes to the graphs also. So we have to worry about that and think about that. They just didn't do it for the tables, so I just gave you this simpler format for the table, because that's all they're going to do with you on the tables. But for the graphs, they're going to have a little more going on. Now, the c is almost always 1. I mean, I think there'll be like one question in all your homework where there's even a number there multiplying the base that's not 1. It's almost always 1. Like this one, it's 1. How do I know? Can you look at that thing and identify the A, B, and C? Oh yeah, everything's 5, huh? So here, let me bring it down here. So 5x plus 5. This is the A. They've got it in the reverse order that I wrote it, huh? And this, is that 5 the B or the C? That's the B. The C is an understood 1 in the front that we don't really care about. Right? C is the number in front, not the base, right? So that's what I mean by the C is almost never shown because it's really 1. So part of me wants to not even write it. It's really just the A added plus BX that you really have to worry about. So, all right, so looking at it that way, the A, the number added or maybe subtracted if it's negative, is super important, really, really important. When it comes to graphing, A stands for asymptote, and it's horizontal. So exponential graphs have a flat horizontal asymptote where whatever that number added or subtracted off to the right or left, separate from the base is. So plus 5, go up to 5. 3, 4, 5. There it is. So there's the, I'm going to erase this stuff. So there's the horizontal asymptote. It's up at 5. Good to there? So always do that first. Notice this is different than those other 6. Start with the asymptote. That'll really help you. Before, I have no dots yet, huh? Now I'm going to do the dots. I'm going to do the, you know how to do the dots, right? I'm going to do the, make an XY table, put in whatever X value is the center, and then add 1. I'm going to do all that same stuff. But notice first, I found the horizontal asymptote. That'll be really helpful to you. It's the most, important part of the graph. It really guides the rest of the graph, All right, so now you remember how do I find the center? What do I plug in for X? Yeah, whatever makes the X world, and the X world's just X in this case. If there was something like X plus 3 up here, then I would plug in negative 3, to make that little world 0. But it's just X, nothing more than X, so it's just 0. right? So what do we get? Y equals 5 to the 0 plus 5. And remember, don't make the mistake of saying 5 to the 0, 0. Remember, it's 1. That's real important. So 6. So where's that? Over 0 up 6? Right here. Huh. That's up 6. Over 0 up 6. And you know what? Notice it's 1 unit above the horizontal asymptote. That virtually always happens. Virtually. So not always, but almost. You know why? It's the C. When that C is 1, that makes it be 1 unit away from the horizontal. I don't want you to have to memorize too many facts. Just file away in the back of your mind, it almost always is just 1 away from the horizontal asymptote. 1 above or 1 below. So there it is, no surprise, the center point is 1 above. Now I need one other point. How do I find that other point? Add 1, plug it in. When I plug in 1, I get y equals 5 to the 1 plus 5. That's 10, huh? So over 1, up 10, it's way up here already. So it's rocketing up, right? Over 1, up 10. What do you think it's doing on the other side? Well, you know, it's got a horizontal asymptote, so it's flattening out. And there's the graph. So exponential graphs, they always rocket up or down on one side, flatten on the other. So they might rocket up to the left, flatten on the right, or rocket down on the left, flatten on the right, or rocket up on the right, flatten on the left, or down on the right, flatten on the left. So always one side takes off, up or down, the other side flattens. Always have a flat side and a rocket side for exponentials. So expect that general form. Is that good? Questions on that one? So what's the most important part of doing the horizontal? Oh, it's the horizontal. Doing the exponential graph, it's that A, right? That stands for asymptote. It's the number added or subtracted that makes it all happen. All right. What is the horizontal asymptote is y equals 5. You got that. Y equals, hits the y-axis at 5. That's the horizontal. So what's the domain of this? So you look at a graph, domain is left edge, right edge. Negative infinity, infinity, right? Goes forever left, forever right. Up and right. Okay, but what's the range? Range is bottom, comma top. You know, domain was left, comma right. So yeah, so what's the bottom of this thing? How low does it go? 5 with a parenthesis, not a bracket. Never touches the 5, huh? Up to infinity. Good on that? All right, good. Thanks. All right, so number 10. Y equals 2, 1/5 to the x. All right, so as soon as you see, how are you going to recognize on the, a lot of the battle in math is recognition, huh? How are you going to recognize this on the exam next Wednesday, Thursday, as an exponential graph? What tells you? X is in the power zone, right? So it's not just that it has powers, but that X itself has climbed into the power zone. That's exponential. All right, so you go, all right, exponential. First thing I need is horizontal asymptote. Got to find the horizontal asymptote, right? That's always the first step. Horizontal asymptote. Step number 1 on an exponential graph. So, what is the horizontal asymptote? Yeah, it's whatever number's out here added or subtracted, which is nothing. So this one has a 0. So right away, go to your graph and put a horizontal line right on the axis because it's a 0. So they always have one. They always have one. If there's no number added or subtracted, it's 0. That's the A. All right. Now you know what to do from here, right? Now we do our XY table. Oh, look, this one has a C value that's not 1. Remember I said you'll almost never see 1 with this. Here we go. Here's our second problem. The C value is 2. So anyway, doesn't matter. We can you don't need to worry about all that stuff. You don't need to memorize all that stuff. I'm kind of a memorization minimalist. All you need to remember is the horizontal asymptote. Now just make the table. Find the center point. I'll let you do that. So what do we plug in to find the center point? 0. So we get y equals 2, 1/5 to the 0. Anything to the 0 power is 1, so that's 2 times 1, which is just 2. So y is just 2. So over 0 up 2. Notice here's a case where the dot is not just 1 off the horizontal, it's 2. Why is that? Because the c is 2. It's totally a weird, rare problem, even though it's only our second problem. Seth?
For exponential functions, the range will never be all real numbers.
Right, the range is never all real numbers. It's always limited in its range. So there's the center. Add 1, plug in 1. What do we get? 2, 1/5 to the 1. So that's just 2 times 1/5. Just use your calculator. What is that, 2/5? 0.4? Isn't that 0.4? Just you get a decimal, you know, because you're just graphing. Over 1, up 0.4. What's that? Well, a little below a half, about right there. Right? Over 1, up 0.4. This is over 0, up 2. Is that good, how I did that? Just use decimals when you're graphing, because you just want a dot and know the general vicinity. I'm fine with decimals. Or fractions, whatever. As long as you know where the dot is roughly, you know. Is that good? Now, remember, they always have a rocket side and a flat side, right? Always. So you can tell, huh? It's flattening to the right, isn't it? It's coming down. So that must be the flattening side. That's why these 2 dots give us all we need. It must rocket on the other side, because they always, exponentials, have a rocket side and a flat side. This is the rocket side. This is the flattening out on the asymptote side. We can tell by the 2 dots. Is that good? So if you want more, sometimes people have a lot better memory than me, and they like to just memorize things. So if that's the case, yeah, that c value will always tell you how far off the horizontal asymptote. It will, if you want some extra facts that you can remember. That will work. All right, you want to try that one? Let me let you do a couple steps there. You'll see it. 5 to the x plus 1 plus 2. Yeah, the 1's up there in the power zone. Yeah, with the exponent. True and important observation. So give it a try. What do you do first? Horizontal asymptote. What's the horizontal asymptote? 2. So put that on your graph. So yeah, the asymptote's at 2. It's always horizontal. Right there, that's the asymptote. All right, then we make our xy table. What do we plug in for x to find the center? What do we plug in? -1. Yeah, because you look at x's little world, right? You plug in what will make x's little world 0. That's how we do all these graphs when we find the center point. So -1, so if you plug in -1, you get 5 to the -1 plus 1 plus 2. That's 5 to the 0. And what's anything to the 0? 1, yeah, don't forget, that's not 0. So 3. So back 1, up 3. Look at that. See how that dot is 1 above the horizontal asymptote? That's because the c here is really 1, huh? Positive 1. All right. Add 1, so that'll be 0. Plug in x is 0. You're going to get 5 to the 0 plus 1 plus 2. That's 5 to the 1 plus 2. That's 7. Over 0, up 7. So 1, 2, 3, 4, 5, 6, 7. Over 0, up 7. This one was back 1, up 3. So we got our 2 dots. You know, it rockets on one side, flattens on the other. So it must be rocketing this way, flattening that way. Huh? Good? On all that, questions? Getting the hang of these these exponential graphs? All right, let's look at that one. So we've got y equals 3 plus e to the minus x over 2. All right, now it's time to talk a little bit about e. What is e? It's just a special number, right? Don't think you need to do really crazy things with e. E is just a special number. Just like pi is a special number, right? Pi is 3.14, whatever, right? E is a special number. It's 2.718, blah, 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 blah. It's a special number. In calculus, you'll see more what it's for. It's the perfect number to make a function its own derivative. It's the exact number that makes that happen. It's very useful also for continuously compounded interest. Anyway, there's some real life applications. It's just a number we discovered, just like pi is. It's just part of the warp and the woof of the universe. It's just how things work. Like pi is the exact radius of circumference to diameter for every circle. They just discovered that back in the Egyptian days. They were finding little circles and big ones, and they were measuring around them and across them, dividing those numbers and going, we almost always get like 3.14, or depending on how accurate their measurements were. Right? And so after a while, it became known that any circle, all the way around, 2 pi r, divided by 2r is pi. Right? It's 3.14. Anyway, so pi was discovered. E was discovered later in the same kind of way, having to do with continuous compounding interest and derivatives. Anyway, all we care about for now is it's a special number. So when you look at this, don't think, okay, it's E, I've got to do something crazy. Just think, E's like 2 something. It's kind of like that. Just think that way. It's like that, except E's, 2.7 whatever instead of 2. Does that make sense? I just want you to get that first basic principle. E's just a special number is all it is. So, all right, so this is exponential, not because E's involved. That's not what makes it exponential. A lot of people think that way. Oh, E means always exponential. Not necessarily. Why this is exponential, though. Why is it exponential? Because the x has climbed into the power zone. That's what makes it exponential, even if there was no e involved, right? All right. So with that in mind, let's just do the regular thing. My main point is it's regular, So regular, what do you do first? Asymptote. It's at 3. 1, 2, 3. There it is, positive 3. They can be negative. We haven't had any negative ones yet. Like if that 3 was subtracted at the back or something, that'd be a negative 3. That'd be down, the horizontal asymptote down 3, Just haven't had any of those, but they do exist, and they will be in your homework probably. All right, so up at 3, it's the horizontal asymptote, and then we just go make our XY table like regular. And what do I plug in for the center? 0, because here's X's little world, and what will make that little world 0 is 0, right? So y will equal 3 plus e to the minus 0 over 2. E to the 0, right? 0 over 2 is just 0. Negative 0 is just 0. What's anything to the 0? 1, so that's 4. So no surprise, look at that. The dot is 1 off of the horizontal asymptote. Of course, because right there the C is 1, like it almost always is. So there's the center dot, 1 off the horizontal, like always. What do we do now? Add 1, like always. So plug in 1 in, y equals 3 plus e to the minus 1 over 2. That's a little ugly. Just use your calculator. Just hit the buttons on you. That's why you want to have a scientific calculator, definitely, next Wednesday, Thursday, because this will be on the non-graphing part. Obviously, it's a graph. I'm not going to put this on the graphing calculator part of the test. You would just hit the buttons, right? But that means you're going to need to do this kind of thing on the non-graphing calculator part of the test. So you want to have your scientific calculator with you, unless you just know exponential to negative fractional powers off the top of your head, right? All right, so I have no idea what it is. It's one of a screw to be, so I don't know. It's like 3 point something. I know that much. Somebody have it for me? E to the minus half? 3.71. 3.71, thank you. So I'll just say 3.7. That's as accurate as I can graph, right? Over 1, up 1. This is up at 4. 3. So my point is it's come down, right there. It's come down a little, hasn't it? From the other one that's over 0, up 4, right? It's come down, which tells me it's going down to the right. Remember, because it always has a flat side and a rocket side. So this must be the flat side. This must be the rocket side. It's important that I found 3.7 is lower than 4, so it's coming down to the right. Can you guys get that 3.7 on your calculator? E to the minus half power. I would just go 3 plus e to the minus 0.5. I'd probably choose a decimal. Make it easier, E to the minus 0.5, add 3, 3.7. Good with that? That makes sense? So it's really not anything new. Just got to use your calculator in the last step. E is just a special number. Questions? We good? All right, so 2 to the minus x is 4. 2 to the minus x is 4. All right. How do we solve that? So here's the plan. This is an x. We're changing gears now. We're done with graphing. Now we're looking at an exponential equation. Now, as we want to solve, it's an exponential with an equal sign and a left and a right. It's an equation, right? So what do? Step one, make the bases the same. Funny looking S there, same. And then set powers equal and solve. So the game plan is to make this 2 and that 4, the bases, be the same number. So how can I make them the same number without changing any actual values? You know. What do I do with the 4? 2 squared. That's still 4, but now the bases are the same. Make sense? So there was step 1. Make the 2 bases the same. And once you've done that, you can do step 2, which says just set the powers equal. And then so x will be -2 on the next step. But does that seem logical? Does that seem reasonable? First step is I made the bases the same. 4 is 2 squared, so that's legal. Right? And then once you've made the bases the same, the powers have to be equal. Because if 2 to something is equaling 2 to something else, those powers have to be the same. Because if the powers were different, then 2 to one of them wouldn't equal 2 to the other. Does that make sense? The powers have to. Once you've made the bases the same, if those things are equal, the powers have to be the same too. Don't they? So then you can legally, reasonably, logically set the powers equal, solve for x. -2. And that makes sense, huh? If you plug in x -2, you'll get 2 to the -2, which will be +2, which is 4. Sure enough, that's the answer. Probably could have guessed at it, huh? They'll get too hard to guess in a minute. Is that good? So we'll need these steps. Good for there? That's how we're going to do a bunch of these, and it's all going to be the same way. Make the bases the same, set the powers equal. I think, but we'll do it quick. Okay. 3/5 to the x is 27. They're just giving you big numbers. Can you tell? You guys have your calculator with you? Do you know what power on a 3? Just take the 3. Just forget about the 5 for a minute. Just 3 to what power? 3 how many times makes 27? 3 times. And is 5 3 times 125? Yeah, so the answer is just 3. Just use your calculator. It's just nothing fancy on that one. Okay, good. Okay, so 3 to the 5x plus 1 is 9. Try that one. So go through those 2 steps. Step 1, make the bases the same. Step 2, set the powers equal. So make the bases the same, then set the powers equal. All right, so this is 3 squared. So that's step 1. Step 2, powers have to be equal. Right? Those powers have to be equal, or because 3 to one of them wouldn't equal 3 to the other if the powers were different. Right? So the powers have to be equal, and then you can just solve for x. 5x is 1 divided by 5, 1/5. Good. All right, so 3 to the x squared is 81. Same thing to the x. Set the, make the bases the same, then set the powers equal. I'm going to make it a little smaller, so there's going to be more steps. So 81, use your calculator. It's 9 times 9, and that's 3333, huh? So it's, and the x is still there as well. So I just made the 81 into 3 to the 4th. If you're not sure, use your calculator. Go 3 times 3 times 3 times 3. Keep count. Or use the power button. 3 to the 4th is 81. So I made the bases the same. Use your calculator. That's why you want to have your scientific calculator on the first part. I think these are on the first part. So I just made the exam yesterday. So yeah, these are on the first, where you don't get your graphing calculator. So you're going to want to you have your scientific with you. I'm not part 1 on next Wednesday. All right, bases and step 2, powers must be equal. Because if 3 to something is equaling 3 to something else, those somethings must be equal. Now we have to solve that. Can you solve that? So let me give you a second. So when you see an x squared, do you know what to do? When you see x squared, number 1, you get a 0. And then you factor. Remember that whole thing? So subtract 4. Whoops, that's a minus there. Subtract 4x from both sides. Get a 0. And then factor. How do I factor? Take out an x. Right, remember all that? That's what we always do when we have x squared. And then each one equals 0. So it's just 0 and 4, huh? Those are the 2 answers. There's 2 answers on this one. X could be 0 or x could be 4. We good? So make the bases the same, set the powers equal. Okay, this is a valuable one. 64 to the 5x is 16 to the x plus 4. All right, so make the bases the same. So use your calculator. This is important, guys. I know we got a minute and a half. I'm going to use that. This will be for your benefit. This one has an important lesson. Use your calculator. So what you should look at first, naturally, and wonder, is the higher number 64, is that like 16 times 16, or is that a bunch of 16s? And the answer is no. If you take 16 times 16, that's way too big. Something like, I don't know, something big. It's not 64. So then you go, what do I do? You can't make 64 out of 16 to something. So what do? You make them both out of 2 or 4, either one, doesn't matter. Whatever you work. Yeah, make them both out of something smaller. I'll just do 2. How about? You can do 4. You're right, you could do 4. 4 would be easier, huh? So let's just do 4. So you gotta test the 64. 4 to what power is 64? Use your calculator. It's third, huh? So 4 to the third. And the 5x is still there also. And the other side, 16 is 4 squared. See how we made both bases the same? So this time we had to change both of them, right? Sometimes you have to do that. So there's step 1, make the bases the same. Now, step 2, and then I got to distribute that. So that'd be 4 to the 15x. Remember, powers outside multiply powers inside. 2x plus 8. So we made the bases the same. Now step 2, set the powers equal. So 15x must equal 2x plus 8. And solve. Subtract 2x. Boom. 13x is 8 divided by 13. There it is. 8/13. Darn, I knew we weren't going to get through this. We're going to go really fast tomorrow. Man. All right, this is not due, unfortunately. All right, we'll go fast tomorrow.